Hey guys, in this video we're going to talk about the concept of angular momentum. So as with most things in rotation, angular momentum is the rotational analog of linear momentum, where you may remember linear momentum is represented by the lowercase p, and we say p equals mv. And so since it's the rotational analog, instead of m, we're using moment of inertia. And instead of a linear velocity, we're using an angular velocity. And so now suddenly that's angular momentum. I really can't explain why it is the letter L with an arrow over it. No accounting for that. Also, though, there is another formula for angular momentum, which you can see represented over to the right here. And I'll explain how we use each of these formulas and how they are related to one another. Okay, so first and foremost, understand that something obviously has angular momentum if it is rotating around. All right, so if you have something like a merry-go-round and it is literally, say, spinning, right, about, some kind of an axis like, say, the middle, then obviously it has angular momentum according to the equation I omega. And if it's got a larger moment of inertia or it's spinning faster, then it's going to have more angular momentum. Okay, so that's very straightforward. The mv cross r over here, though, is what we would use for something like a projectile that has angular momentum. A projectile can be said to have angular momentum under certain circumstances. Okay, so what are those circumstances? Well, let's ponder for a moment a merry-go-round. So here's a merry-go-round viewed from above. I mean, sort of. And consider that there are children who are perhaps going to try to jump onto said merry-go-round, as children do. We will model these children as point masses. Viewed from above, that of course makes them a sphere or circle or something. Anyway, this child is going to go jump onto it. Since momentum's in the title here, you might imagine that angular momentum is going to involve collisions and explosions, and you'd be right. Sometimes after collisions and explosions, things spin in addition to, say, moving in some direction. So if this child here comes running along and then jumps and lands, say, on the edge of the merry-go-round, the very edge of it, just, barely holding on to it, right? This child has angular momentum, which experientially is true, because if he jumps on in this way, he's going to make the merry-go-round spin, right? After he lands, there will be spinning. The initial angular momentum of the system before the kid lands on the merry-go-round is all right here in the child. But Mr. Errico, the child is not spinning. Okay, that's true, but according to this formula, the child has angular momentum because of where he is going to land on the merry-go-round. The merry-go-round must pivot around the middle. And so if this kid lands at some distance r here at the edge from the pivot, and he is moving, which he is, then he has angular momentum, because we understand that the tendency of him landing on the edge is going to be for the merry-go-round to begin to rotate after this collision occurs. Okay, all right. On the other hand, another child who jumps on, say, like this, even if they land right here, we understand that they do not make the merry-go-round spin, because if you continue this line of their velocity, it actually passes, directly through the pivot. So this child, the mv cross r, has a value of 0 because his velocity runs straight through the pivot. Said another way, his velocity vector is parallel to the radial vector drawn from the pivot to the point where he is going to land. And given that the velocity and the radial vector are parallel, there is no angular momentum from that child. On the other hand, the one that landed on the very edge, there's the radial vector and there's the velocity vector. Those are very much perpendicular. And so that child that lands on the edge is going to have a lot of angular momentum, because if you recall, mv cross r means mvr sine theta. And therefore, the more perpendicular V and R are to each other, the greater the angular momentum is going to be. All right, so again, to review, I omega is usually used for rotating solids. MV cross R is usually used for projectiles. And there are a few broad categories of questions that we're going to be able to look at with these two formulas. Some you'll relate one to the other, others you'll only use one type or the other. All right, let's look at one such example. So find example 7 in your notes packet. If you somehow don't have your notes packet, then pause me, take a minute, and read the question. Basic idea is we've got an astronaut. He's going to throw a wrench to try to save his life. Poor fool is drifting away from the space station, and he wants to drift back towards it instead. All right, let me draw some pictures. All right, so here's a picture that shows what the astronaut hopes in his desperation will happen. If he throws the wrench, then he's going to drift back towards the space station. Wonderful. All right, but now part A is giving us some kind of a hint that something is going to go maybe dreadfully wrong here. He might drift back towards the space station, but the problem is that because of the way he's thrown this, and it's maybe unavoidable, but because of the way he's thrown it, the velocity vector exists at a separation r and at a nearly perpendicular angle from his center of mass. And so, therefore, the wrench has angular momentum. All right, and so the result then is if the wrench has angular momentum, then he has to acquire angular momentum afterwards and is therefore, you guessed it, going to start having to spin like that. All right, so let's set up some equations that are going to help us understand it. First thing is momentum and angular momentum, even though they both involve the word momentum, are different. They are separate. They are, in fact, unrelated. Here is the equation that I might write for conservation of momentum. All right, fine. Note that before he throws the wrench, the system has linear momentum because he's, of course, as we said, drifting away from the space station, which is unfortunate. On the other hand, beforehand, there is no angular momentum. Initially, nothing is spinning. Nothing's being treated as a projectile about some sort of pivot. So initially, there is no angular momentum, right? Neither in the I omega sense, nor in the MV cross R sense. On the right side of the equation, though, the wrench has MV cross R of momentum, and the astronaut has I omega of momentum because he will be rotating after this explosion. All right, well, part B wants to know about his angular velocity after he throws the wrench. So let's put in the relevant quantities. We said initially no angular momentum. Afterwards, the wrench is 1 kilogram. He throws it at 20 meters per second. Okay? And importantly, he is 1.8 meters tall, and we're putting his center of mass right at his waist, which, by the way, anytime something rotates, assuming that there's no pivot to constrain it, it will rotate about its center of mass. Okay, so that means that if he's 1.8 meters tall, r, the distance that the wrench is from his center of mass, is going to be 0.9. Obviously, I'm making some assumptions about how he throws it, like he throws it from literally the top of his head. Maybe that's awkward, but whatever. It's an idea for how we ought to go about modeling this. Okay, all right, and then we have plus, all right, I, moment of inertia. Our instructions were to model him as a uniform rod, all right, questionable, but all right. Rotating about his center. Why the center? Well, because there's no pivot constraining him. Therefore, he will rotate about his center of mass. So 1/12 ml squared. His mass is 100 kilograms. And the length of the rod, that would be the astronaut, is 1.8 meters. Okay, and then here we have omega. Okay, so a little bit of algebra later. And assuming I didn't make any typos, I'm getting 0.667 radians per second. Okay, all right, that's how fast he's going to be spinning after throwing it. Now, notice how fast he is spinning is going to largely depend on, okay, fine, a couple of things, but how fast he throws the wrench, but also where he throws it from. So if he throws it from up by his head, R is going to be a large value, and therefore he will spin faster afterwards. On the other hand, if he manages to, say, somehow throw the wrench from, like more like a chest pass kind of a thing, well, then he won't be spinning quite as fast afterwards because the R is going to be a smaller quantity. Okay, now on to his linear momentum, because that's what part C wants to know about. C is saying to find the speed with which he's moving back towards the space shuttle. All right, for that, I want my momentum equation. Please note, for example, I can't just do this. This is always very tempting. People want to be like, oh, yeah, so V equals omega R. So, you see, I will just plug in the omega that I got, and then I'll plug in, I guess, 0.9, because that would be the radius. No, guy, whoa, hold on here. Doesn't work. Is he rolling through space? No, he's not rolling through space. V equals omega R works just fine if you have something like a rolling object and you want to relate its angular velocity to its linear velocity. For a rolling object, those ought to be connected as long as the rolling object is not, say, slipping. On the other hand, the speed with which he translates backwards is actually unrelated to his angular velocity, completely unrelated. Okay, so if I'm doing momentum here, on the before side, note that he and the wrench are both moving at 0.1 meters per second to the left. Okay, well, I'm going to call that, how about negative 0.1? I don't know, I had to pick something. Also notice that means that, the combined mass of the system is him and the wrench. So that's 101 kilograms. That's the left side of my momentum equation. On the right side, they are now separate. So we have the wrench, moving to the left, so negative 20. And then we have the astronaut, moving with some unknown final speed that we're supposed to calculate. And again, a little bit of algebra later, that's... All right, again, I hope I didn't make any mistakes there, but that's how fast he'll be hopefully drifting back towards the space station, assuming, obviously, these numbers are reasonable. All right, now, the last part of this question wants to know, are the linear and angular momentum affected by each other? The answer is really no. They have no specific relationship. They are quantities which are conserved independently. Notice nowhere in the momentum equation do I care about like his moment of inertia. It doesn't matter if I treat him as a solid sphere, as a solid cylinder, as anything at all. His moment of inertia is irrelevant. Also, it doesn't matter whether he throws it from up here by his head or whether he does just like a straight up chest pass or waist pass or something. Anyway, throws the wrench from a different spot. None of that matters when we're doing his linear momentum. On the other hand, for his angular momentum, all of that is important, right? We had to worry about exactly where was the wrench being thrown from, and then how do we model the astronaut, right? Is he a uniform cylinder, a cylindrical rod? It's a questionable assumption, but we had to pretend he was something to avoid immense complexity. Fine. Either way, though, the moment of inertia and the distance from the pivot where the wrench was launched from both matter for getting his angular velocity, but are irrelevant to his linear velocity. So linear momentum and angular momentum are two quantities which are both conserved during collisions and explosions, but they are conserved independent from one another. Let's take a look at another common example.